CLI and a cross-platform IDE for C and C++. Download now.
So, I fixed move semantics. This is a what's the word? Clickbaity kind of title for sure. Yes, please go to the Discord. My name is Jason Turner. Phil already introduced me. I already have my intro slides ready to go, of course. And if you don't know this, that's partially because when you get introduced by someone else at a conference, their introduction never actually ends up in the YouTube video for that talk. So I have my own introduction slides to make sure those end up in the YouTube video as well. But yeah, I have been producing C++ Weekly for 520 some odd, whatever it is, weeks now. And I did just recently take back over CVP Cast. And this is exciting for me to be interviewing people again. I am an author. I've got a bunch of programming books for C++ best practices. I also have puzzle books that I've been working on for several years now. And I have a bunch of GitHub repositories you might want to check out. I'm a Microsoft MVP. And as Phil said, I do travel and training, and I'm doing the full conference schedule this year. You're already at C++ Online. You should upgrade your ticket to a workshop ticket, and you should attend one of the workshops that's going to be coming up post-conference. I think they're on average about a month after the conference, something like that. Sorry, I'm reading the comments in the Discord here. This is a QR code, whatever, if you want to go check out my website. All right, this is great fun because, you know, I always have this slide. It says avoid sitting in the back. Well, I don't know where you're sitting currently in the room, but I guess that doesn't really matter. Do interrupt and ask questions. I will be paying attention. And like I said, you can't really yell things out, but that's all right. We will see them in the Discord. So as I was tweeting about this, is that Twitter? Yes, that's Twitter. It's hard for me to keep track of all the things these days. I posted this. The only way to see how I fixed move semantics is to come to C++ Online next week. And Patrice said, I want to know what was broken. So we're going to cover what was broken. An alternate title for this was fixing move semantics. But like I already said, I was going for the clickbait title. So it's something like this is the title of this talk. I am a C++ trainer, as I already said, and as Phil already said. And over the years, I've seen that there's a lot of confusion around R-value references and move semantics. I'm presenting a solution. The solution has not been submitted to the committee, just so you know. Like, I know that's like standard library is how this talk was categorized. I have not submitted this to the committee or anything like that, although it's possible someone would submit something like it. And like all of my talks, I'm not trying to sell you a solution. I don't expect you to use my solution. I want to inspire you. And that's really the goal of every single thing that I do in the C++ community is I just want you to think the next time you write C++ code instead of keeping doing the same thing that you've always been doing. All right, what is this? What is this thing? This 2 ampersand thing that's on the screen, what is this? This is where we wait until you post things. And, okay, an R-value reference, the way some people spell and, it depends, says Patrick. It depends. That is a good answer. Oh, universal reference. That's an interesting one to say. So I think we've hit the 3 possible things it can be now. And that is the logical and, an R-value reference, or a universal reference, or a forwarding reference. If you don't know the history of this, basically Scott Myers called this thing a universal reference, the 2 ampersands, in the case of this forwarding reference situation in his Effective Modern C++ book. And then Scott retired, and then the community overruled him, and they said, no, this is a forwarding reference. That's basically what happened here. All right. I thought I wrote the slide. It's the operator with the most meanings in the C++ standard, but that's not actually fair. because the single ampersand also has 3 different meanings that I can think of. And that is the L value reference, the bitwise and the dereference operator. So there might be other operators with more than 2 meanings, I guess. Dot operator. Are you saying dot operator has at least 4 meanings, Phil? Or the asterisk? Oh, I see. Okay, yes. Has at least 4 meanings. The asterisk. It's also dereference, a multiply, unary. No, wait. Yeah. Well, then it's the same thing. Unary, binary, multiply, overload, address of. Oh, part of a C-style comment. Okay. So let's take a quick look at these 2 ampersands. Do I immediately know by looking at this line of code what this is? Logical and? Could it be? It might be a logical and. It might be anything. Impossible to know just from this to these, what, 1, 2, 3, 6 characters here. There's just no way to tell from this information. All right, so this is the logical and. And yes, I am using print here. If you watched one of my recent YouTube videos, I decided to use print here. And this thing is going to print false in this case. The result of the expression is true if both operands evaluate to true, and the logical and is short-circuiting, assuming you did not do an unwise thing and overload it. It's the sorry, every time you hear me laugh, it's because I've looked back and I've read the comments. So this is going to be confusing for the people who watch this on YouTube in the future, but this is how we roll when you're at one of my talks. Yeah, this thing's going to short circuit if we haven't overloaded ourselves. It can be written as X and Y. Right, Ben? It can be written as X and Y. You could do, I don't know, show of hands or something. Like, who actually uses the and alternative token here instead of ampersands? A few people do. All right, cool. I'm starting to like it more lately. Yeah, I probably should. A show of hands. Thank you, Phil. So a quick aside on references here. Oh, I didn't know it was possible. No, it is totally possible. You can do it with and, or, XOR, bit and, bit or. What are they? There's like 6 of them or something like that. And not. I do use not now more often as well. All right, so a reference is not an object. It is something that literally refers to another object. A pointer is an object that may or may not point to another object. So that there's no confusion here, creating an invalid reference is actually undefined behavior itself. So you don't ever create an invalid reference, but pointers can point to basically whatever they want to. We don't have undefined behavior until we try to dereference that invalid object. An object is anything that is not void, not a function, and not a reference, according to the standard. So we never got regular void. That was something that was proposed a very long time ago now. And functions are not objects. Closures are objects. Function pointers are objects, but functions themselves are not objects. All right, so what is printed here? I am using a reference, I am manipulating an object, I am printing things out. What is the result that is printed? Okay, we're seeing a general agreement that 2 is what is printed. Yeah, so I have x is equal to 1. I get a reference to x. I call that reference y, and I increment y, which by nature is incrementing x. I print x, and I have the value 2 printed. I've done something slightly trickier here, and I ask you again, and now what is printed in this example? Let's see. Yeah, this is a good example. All right, so 10 or 11 seems to be the answer. 10 or 11. 10s, I think, are winning at the moment. So y is a reference to x. And then I change y. Now I do y equals z. So at this point, I'm actually assigning x the value 10. Then when I increment z, I'm just incrementing z. Y has not been changed, nor has x been changed. I cannot reassign what a reference refers to. So this should be 10 that's printed. Yeah, you cannot rebind references. Wait, y equals. Yeah, okay. So everyone agrees here. All right, good. Just making sure, following along in the comments. Okay, what is y now in this situation? Or what are these double ampersands doing? Yes, this is an R value reference. And I just formatted it like this to confuse you. But I didn't confuse any of you, so that's slightly disappointing, honestly. It can also be written like this. I can put x and y here, and yeah, but see, we don't do this because it is confusing and silly, okay? Don't do it. I had to put it in here, and I'm really glad Ben is here because I know he personally does not like this. Yes, Ben, it is not a straw man. I'm just acknowledging the fact that it is there. I do not recommend doing this at all. All right, so what is an R value reference? What does this code to? I have x, I'm assigning it to 42. I have int with these two fun ampersands, y equals x. Yeah, I'm gonna sit here and wait for a minute while you all stare at this. All right, bind temper of x. Oh, there's a question of does it compile? And I see a couple people agreeing with this question, does it compile? And no, it does not compile, in fact. It fails to compile. Why? Does anyone know why? You're confident, but do you know why? Several people are typing. It's an R value on the left because you can't, wait, what was that? Can't bind an L value to an R value reference. That's a good answer there. Yeah, I don't have warnings as errors here at the moment, so we're not going to get just the W unused. Actually, would we get an unused warning on this? It doesn't matter because we can't test it at the moment. All right, no, an R value reference can only bind to an R value. That's basically the answer here. And x is not an R value. This is why move exists. It is a way of converting an L value to an R value. It is an explicit cast to an R value reference type. And that result of that cast gives us an R value that can bind to this R value reference thing. So these things are morally equivalent. I can do a standard move, or I can do a static cast to an R value reference of type int. I'm accomplishing the exact same goal here. We're gonna get to forward, Patrick, not yet. We will get there in a little bit. How much time do I have? That's fine. I can do this for a couple of hours still. All right. So what is move? Just go ahead. What is move? This is better when people can actually yell. It is a cast. All right. It is a cast to what? It is a cast to an R value reference. All right. So why do we have move? Oh, an R value. I'm not wearing my pirate t-shirt today. Why do we have move? The point of move is to select which overload we want to call. That is the ultimate goal of using move. And how does it select said overload? By casting to an R value reference. Now we will have a series of these, and I think this will work all right. I have these 4 lines, and I'm asking on A, which thing is called 1 or 2? On B, which thing is called 1 or 2? On C, etc. So you could possibly quickly type out A1, B1, whatever, and we'll see what these answers look like. So looks like we've got a few A1s and a few A2s and a few B1s. All right, we've got more answers coming in. A2, B1, C2, D1. A2, B1, C2. No, let's see. C2, yeah, okay. All right. That seems to be what the room is settling on here. So on the first version, we are calling the version that takes a const L value reference. On A, we're calling 2. On B, we are explicitly casting this thing to an R value reference. Therefore, we're going to get the R value reference overload, and we're doing that with move. So we'll get number 1 called. And then for C, we are casting to an L value reference. That's kind of pointless, but it is going to call the const int reference version. That's number 2 again. So there we are. It seems okay. Everyone is kind of settled here. We've got 2, 1, 2, 1. All right, I have now changed this to a const auto x equals 42. Let's play the same game again and tell me which function is called on each of these A, B, C, D. So most people are saying that in every single version, I'm going to get 2. Oh, wait, hold on. Someone said compilation error on lines 11 and 12. All right. So, very good. Error on line 11. Okay. Some people trying to make a point of not calling out too many names for the sake of the YouTube recording. No, we're not going to do a const cast. No, stop it. No const cast here. This is not an option today. So that is true, Ben, that x is a constant expression, but that does not actually affect the meaning of this code. On line 9, I am calling the const reference version. On line 10, for B, I am calling the const reference version again. And as some of you said, lines 11 and 12 don't compile because I can't remove the constness. So move is not just an unconditional cast to, well, it is an unconditional cast to an R value reference of the given type, but I was giving it a const integer. So the result of move for B is actually a const R value reference, and we'll actually see what that looks like more in a moment. There's very few cases where we intentionally use const R value reference in our code. All right, another version, I am now passing just the literal 1 to this function. Which one is going to be called? Okay, everyone is agreeing 1 in this particular case. You know, I have to be honest, I actually had to like fact check myself as I was writing the slide, because I'm like, wait a minute, what's the possibility that I can't get an R value reference to an integer for some reason? But you can right here. I can get a R value reference to an integer. That's why you thought line 10 wouldn't compile back here. Is that what you're saying, Keith? Yeah, it just gives you a const R value reference, which then decays to a const integer reference, to an L value reference. And that's something we'll talk about in a moment too. So temporaries are our values. Move constructors and copy constructors. Okay, I have now just given us the words to talk about here, if you will. So I have A and B again. I'm asking which constructor is called on line 13, which constructor is called on line 14. Now, both of those things look like assignments, but they are not. They are initialization, and that is because I am declaring the object at the same time that I'm giving it a value. This is a constructor that's going to be called. This is not an assignment operator that's going to be called. All right, so we have A as a copy, B as a move. So I'm trying to really get you to all be on the same page here, that the whole point of move is overload resolution. That's why we use move. We're selecting which version of a function we want to call. In this case, it happens to be a constructor. Often it's a constructor, sometimes it's an assignment operator, sometimes it's some other completely arbitrary function that happens to have R value and L value reference overloads for it. That's all we're doing, is we're selecting which version of the thing we want to call. Yeah, everyone is, no assignment. No assignment. Construction. Because it's still a new object declaration. So copy constructor, move constructor. All right. I still am not actually pulling the assignment operators in here, but I've got 3 of these things. So I have this R value reference that I'm creating here. First of all, you know, like, yeah. I just realized what I did there. It does create an L value reference. You're right, Patrick. I tricked myself on this particular one. We haven't even talked about forwarding references yet, and I confused myself with it. So no, we're not getting a constructor on line 12. That's true. And we are getting, the question is, what are we getting on line 12? And I did confuse myself, as I already said. So no constructor, reference of the same type. That's what we were saying here. B is copy construction. So object2 is a reference, but it's not an R value. And where I confused myself and what I will now demonstrate here is I was thinking that I had made an R value reference here. But as we know, if I made an R value reference here, that would not compile. That was actually a universal reference or forwarding reference. And so if I do this, this is actually, I think, the version that I meant to show you, unless the next slide has it. And let's look at this version here. So on line 12, I am creating an R value reference to object. Now then the real question becomes, on line 13, what am I doing when I take this R value reference and I initialize a new object? That's really the question I want to ask you. Yes, that is definitely a copy. And it is a copy because this thing that we've already talked about before, object2, is an L value. It's not an R value. It's an R value reference, but it's not an R value. It's not going to bind to the move constructor. It's going to bind to the copy constructor. This is like kind of confusing and annoying. And even though I've taught it like 100 times now, it's confusing. The words are difficult to use here. An R value reference itself is an L value, as you're saying. So if I actually want this thing called object2, which is an R value reference, to call the move constructor, I have to call move, if you will, on that thing again. I have to static cast it to an R value reference again to get an R value so that I can select the move constructor overload that I'm looking for. Yeah, right. This is okay. So, you know, this is my argument for like how are move semantics broken? This is how they're broken. The terminology is very difficult around this, and it can be difficult to communicate these things, and which things are called in which situations don't tend to be obvious to most readers. Excuse me. I'll let the comments settle down for a moment here. Basically, as soon as you give it a name, it's an L value. That's a fair way to look at it. All right, I'm going to, I think, move on. All right. All right, so there we go. Now, oh, this is a great one. This one is super fun. The question is, which constructor is called on A and which constructor is called on B? Now, keeping in mind that if you don't declare these copy and move operations for you, following a certain set of rules, the compiler automatically generates them for you. Yeah, you remember the table. The table is there, yes. So always a copy, that's what I see. Yeah, copy for both because defaulting the destructor disables the implicit move generation, which is correct. In fact, that is a very accurate way of stating that. So the fact that I mention the destructor at all has the compiler say, I'm not going to generate these move operations for you. So I'm getting actually the copy constructor called in both of these cases, which is really annoying. Oh, Phil has his own version of the table, except it's on the Sonar source website. So I guess it's Sonar's version of the table. So copy construction. This type implicitly does not have move construction because we mentioned the destructor. But I called move on it. I called move on it, and it's not gonna move. We've already seen if we've got an object that's const, I can call move, and it's not gonna move. I have an object that doesn't have a move constructor, it's still gonna do something. All right. So let's talk about syncing constructors. I'm going to have to move faster. Constructors that accept an R value reference is what I refer to as a syncing constructor. It's one to sync a value, wants to take ownership of this value. Which constructor for a string is called on line 5? Yes, it is the copy constructor. That's all right, so now which constructor is called for this string object on line 6? This is going to be the move constructor. All right, now which constructor is called on line 5? You all should be following along now. That's the copy. So to actually get a move, I have to do this, right? I've taken our value reference, I have to move it again. All right, this is surprising confusing to many C++ programmers. This is one of the main mistakes I see with R values and moves. So why do we want move assignment and move construction? It comes down to basically something like this. I just kind of mocked together a thing. It's something that holds a bunch of data, but we want the copy operation to do a deep copy of the data. So we can give it, default to the move constructor, and the defaulted move constructor will take ownership of that pointer. But if I have to have a copy constructor, then I'm going to have to provide some sort of deep copy mechanism into the thing. So this is basically the fundamental reason why we want move operations. Now we'll get to forward, I hope, soon. So would it make sense to ever define a function like this that takes an integer array by R-value reference? I'd say it's unlikely. I'm going to agree with KOD. And it's unlikely for this function to make sense. Maybe there's not much to be gained here. But if I switch this around and this is an array of strings, does it now make sense to potentially take an R-value reference to this thing? This one is slightly less obvious. Yeah, I'm getting some yeses here. And the yeses are because even though like array itself is stack storage, this is an array of many things that have pointers to steal. So this is a likely thing that makes sense. So the problem with move semantics, most C++ developers don't understand it's just about overload resolution. Most C++ developers don't know that you need to further move an R-value reference to actually get the move operation that you want. And as it's considered confusing enough that there's a 250-page book that's been written about move semantics alone. Yes. I don't have a link to Nico's book here. So I ask, can we do better? And I would say I hope so, otherwise the talk up to this point has been a waste. So what is the fundamental problem and why is this hard to get right? This is something that I just keep coming back to. And I'll see if anyone says, what is the fundamental problem? Why? Compiler doesn't warn us. Naming. No, see? C++ is the fundamental problem. Here, all right, let's see. My big reveal. It's implicit conversions. It's always implicit conversions. That's always the problem. If you've watched any of my talks, it's always implicit conversions. We have an R-value reference to a const L-value reference. We have const R-value reference to const L-value reference being a secondary problem. So what do we do? Stronger types. So I want you to imagine a magical type. This magical type is called a moving reference. If I try to assign it something that is an L-value reference, it refuses to compile. If I assign it something that takes an R-value, that is an R-value reference, it compiles correctly. If I have an object that this assignment on line 8, if I do this assignment, I automatically get move construction without having to call move again. And if I try to move a const object, it refuses to compile again. Let's think of a magical type that could do this. And then use like two other possible use cases, like this, if I have implicitly calls the move constructor on line 6, so this is the other problem. And in this particular case where I've accidentally removed my move operations, it refuses to compile again. It's like, no, I refuse to create a moving reference of this type that doesn't have a move operation. So I think this would solve my problems. And I see some of you taking some guesses at some things in here. So is it possible to create? Is it difficult to create? Mustafa says he thinks it should be straightforward. If we default to the move constructor, then that would compile. Yes, it would compile. And is it backward compatible? Well, we'll get to that in a minute. Is it a complicated type? The magical type needs to be constructible from a non-const R-value reference, and it needs to be implicitly convertible to an R-value reference. And so this is fundamentally what it needs to be. This is the simplest take at it. It takes an R-value reference in its constructor, and it has an implicit conversion to R-value reference of the exact type back out. Fundamentally, that's all this thing needs to do. Some of you should be, there will be some deletes, but they're not necessary, actually. It's interesting. You really only need these two pieces. So in case we run out of time, spoiler alert, you only need these two pieces, and you can get this working in C++11 without concepts, without any, you can still delete some of the other overloads in C++11, and this works. This is a version of it that has this has-move constructor concept in it. And some, well, let's see, sprinkle in some helper type defs, make everything const expert, no except, store a pointer instead of a reference type. That's generally a better choice. And I did do this delete with a reason is C++26. You don't need the reason though, so you can do this. And really the only reason to delete this is to let the user have a better explanation of why they were unable to construct the moving reference. We need to discuss the has-move constructor constraint. We'll get that in a second. And yeah, like I said, the delete is just to get better error messages. And the actual operator here, it's just a static cast internally. I'm not going to use move. There's no reason to make it depend on move. All right, so I fixed move semantics. Obviously, there's still more slides left. The has-move constructor concept. The reason this is necessary is because if you know the type trait is move constructible, which also has a move constructible concept defined in the standard library, this thing is weird in that it asks the compiler, it asks at compile time, is this object constructible from an R-value reference? And in this particular case, yes, this object, this type is constructible from an R-value reference. And it is constructible by calling the copy constructor. So it's just very confusing. I've watched arguments go down at CVPCon about this. Right. So this doesn't help. So I borrowed this from Stack Overflow. And the idea is that this thing, it's this detect move construction thing. It's got implicit conversions to const value reference and an R value reference. And this says basically detects if the thing is exclusively copyable or movable. If it is both copyable and movable, then you get a compile time error because that's an ambiguous overload that would be called. And there's a bug in Visual Studio, so this is actually using the assignment operator, not the move construction, but we're going to just pretend like this is move construction for the moment. And so then we define our own concept, has move constructor, that says if the thing is move constructible, which means yes, it is constructible from an R-value reference, and it is not copyable exclusively or XOR movable. All right, we don't have time to unpack all this, but it does work. So that gets us through move, and then we have to get to forwarding references, and hopefully we have the time for this now. A forwarding reference is a template deduced at compile time reference type that can be a non-const value reference, a const value reference, a non-const R value reference, or a const R value reference, depending on what is passed to it. So this is a forwarding reference. This is a deduced type, deduced by the compiler. I pass it whatever I pass it, it's going to give me one of those 4 types of references. You've seen this, I assume. Many of you have, I'm sure. If I put auto here, it is exactly equivalent to the previous template version. The standard actually specifies that this is exactly the same thing as having a template parameter there. This is also a forwarding reference. So it's in the case where I've got deduced by the compiler. If you didn't know this, auto's rules in the standard explicitly say auto follows the same rules as template type deduction. So this is literally, again, the exact same thing. This can be one of those 4 reference types. All right, what kind of reference is now on line 4? Is this a forwarding reference, R-value reference? Is this what? Is this a logical AND? It is an R-value reference, yes. It is an R-value reference because, oh, it depends on T. Oh, that is a good point. That is a good point. No, but yeah, T, that is an interesting point. So if I explicitly create a holder of some sort of reference type, yeah, I could get reference collapsing. We should assume this is an R-value reference, but that's a good point because T could be any type of thing. It doesn't have to be a value type, it could be a reference type. I got that wrong. Oh well. All right. But this is not deduced. It is not a forwarding reference. It's never going to be a forwarding reference. It's going to be dependent on what T was. Now, this is an R-value reference because this is a deduced thing again. And this is what now? Yeah, no, T is not deduced. I'm agreeing with Ben here, but it still could have been an R-value reference. It's just never a forwarding. It could be an R-value reference or an L-value reference, but it was never going to be a forwarding reference. On 2 slides, we're talking conversation 2 slides back now. Yes, this is a forwarding reference. This is something that's deduced by the compiler. And I just want to point out, I bet you actually used more descriptive template parameter names now, don't you? Because things get really confusing when we stick with the single letter T and U and V and W template parameters. Stop doing that. I did that here just to make you annoyed for a moment. This is wrong. So you can't like misuse forward here, but I'm going to move past this slide. This is a fun little experiment that I just came up with while I was working on this. We can pop this into Compiler Explorer, and we can actually see on each line here which version the compiler is generating. So I have a non-const value, const value, whatever, and I can see non-const L value reference, non-const R value reference, const L value reference, const R value reference being generated by the compiler. If you've never played this kind of game before, doing something like this, declaring a template and explicitly not implementing it, and then popping that to Compiler Explorer to see what types the compiler generates is really fun. So to use forwarding references, you have to take the type of this thing. So this thing, value here, this is a forwarding reference. It is using auto. It is a deduced context, or at least can be. You can explicitly specify function template parameters. We just don't tend to do that. Template function template. Ben, you're confusing me now. Parameters. This is kind of ugly, so I don't tend to do this. If I want to forward a value, I don't tend to use auto for the parameter here. I tend to give it an explicit template type name so that I don't have to use duckle type. Function template. Thank you, Ben. Ben did a talk at my meetup the other day, and now I have him in the back of my head. Okay, so I've got my local string. I'm passing it to take. Take is deducing the type of this thing. It's going to get an L value reference, and then I'm just going to do a copy construction on line 3. I have local thing again. I am passing it to take. Now, this is still a forwarding reference, and I'm going to get an L value reference here, but I'm explicitly calling move, which means I'm forcing the move operation to happen. This is not likely what the user of my code expected. They didn't expect to pass me an object and get back something that has been in whatever the moved from state would be, but this is perfectly valid because, as we know, move is simply a cast to an L value, to an R value reference. This is the intended use case for forwarding reference in standard forward. We pass it something, and then it uses the type of the thing to properly forward on that next thing. If I pass it an L value reference, I'm going to forward an L value reference. I'll get a copy. If I pass it an R value reference, I'm going to forward an R value reference, and I'll get a move. That is the goal of forward here. All right, forward. Conditional cast, if it was called with an R value reference, it returns an R value reference. If it was passed with an L value reference, it returns an L value reference. This logic has to be maintained from level to level in the call chain, and it requires boilerplate and is also prone to making mistakes, accidentally getting copies along the way. Patrick, but then I'm always gonna have to do at least one copy or at least one move extra unless I construct the thing in place. So that doesn't, well, we'll get to an example here. So what do we do? Stronger typing. Imagine a magical new type. Do you see where I'm going with this? This is my forwarding reference type. It is a bit wordy. I will give you this. And I don't want to disagree with the value semantics. I just want to talk about the forwarding and move semantics in the standard right now. This is a little bit wordy, so I say I want to take this thing, and if I say a forwarding reference of local, then I know a copy is made. If I take a forwarding reference of move, I know a move is made. And then when I do the assignment right here, it will automatically be, or excuse me, not an assignment, this construction, it will automatically be a copy if it should be a copy, a move if it was given an R value reference. It is a little bit wordy, but it's less error prone. And it automatically forwards. And this automatic forwarding behavior that kind of fell out of the design. I have this take function now. It takes a forwarding reference. I pass it to F2. F2 is expecting a forwarding reference. I don't have to do anything with it. I don't have to forward it on to the next thing, which I would have to do if it were a regular forwarding reference, not my magical type. And then I pass that to F1, and in F1, I'm just going to get whatever is the correct operation that would have happened here on line 5. This is the basic idea for the forwarding reference. It is not very complicated either, same basic idea, but what we do need is we need the deduction guide. Does it blow up if you assign from it twice? And that is a spectacular question, and I'll get to that when I get to the very end of the talk here. So the forwarding, this CTAD, this deduction guide is necessary to do the correct thing. If I'm passed an R value reference, then this becomes a forwarding reference of an R value reference. If I'm passing an L value reference, it's relying on these reference collapsing rules again. See, I thought Phil was going to have a legitimate question. I'm watching him typing, and no, it's not. Walk through these things. Oh, this solves one other problem. This is another thing that kind of accidentally fell out of the work that I was doing on this. What is the thing on line 3? The entire declaration on line 3. What is this? A very greedy constructor, says Ben. It's a forwarding constructor? Is it a move constructor? Is it the copy constructor? Is it a constructor from anything to bad times? Yeah, it is. It's an implicit conversion from anything to bad times. It is the copy constructor. It is the move constructor. Sure, it's the universal constructor. Why not? By using my forwarding reference type, I can get this behavior that I want, where I can take some value that I want to sync by forwarding reference without getting in the way of my copy constructor or my move constructor. This is actually super handy, and I think could clean up a bunch of potential use cases here. Wait, copy constructor still, this is the copy constructor. I'll prove to you that this is the copy constructor. Wait, yeah, BT, that one. So I'm just making a copy of the thing, no assembly generated, bad time, so it doesn't have the default constructor. Do that. And then I can actually see that the compiler is calling something. It's calling a non-const copy constructor templated version of the thing. If I make it const, you're right, the copy constructor is still there. I was wrong. All right, the copy constructor is still wrong. It's still there. You were right. You deserve a prize, but I don't have one to toss to you. All right, it's not good though. This thing is difficult to get right, but the forwarding reference wrapper does the right thing for us. So did I fix smooth semantics? I don't know. We've got some examples and some safety things to talk about real quick. We have a few minutes left. This is interesting and also something that fell out of this while I was playing with it. This is a compacted version of the moving reference design. I am returning a moving reference from this function. This is terrible. And there's no real way to stop me from doing this. Oh, I have no idea what Misra would say about this. And I just also want to say, like, I did make these things explicit and everything else in the final version too. I'm going to switch to Clang real quick. We're going to switch to Clang. Internal compiler error. Let's not switch to that version of Clang, shall we? Okay, we're switching to Clang. And Clang has this Clang lifetime bound feature. So by telling Clang that this reference coming in is lifetime bound, I can now actually get a compiler warning saying that the address of stack memory associated with the local variable I is returned. So using these wrapper types with Clang lifetime bound, I can actually get a safer type of reference than a built-in reference type in some cases. Now, just to be clear, if I was returning a regular reference here, I would also get a compiler error as of C++ 26. So if you want the links, here is the final implementation of the moving ref. I don't know if we have time to actually, well, I'll click on it real quick. Why not? All of this stuff is public domain, but I'll just do a real quick that I have conditionally applied lifetime bound if your compiler supports it. All the things are explicit and no discard, so it's impossible to create one of these things and just throw it away. And it's impossible to get the value back out and throw it away. And then for the forwarding reference, I created a helper take function because that's necessary in some cases. I did not mean to click on that again. Let me know if you want any of these links. I can post them also in the chat. Got just a couple minutes left now. I do have an example that I will click on real quick. Theoretically. And it shows the different ways that forwarding reference can be used. It's whatever. You can put in whatever namespace you want it to be used in. So back to the question of what standard does this require? Moving ref is completely possible in C++11. With C++17, I can get a few extra safety checks. I can get better error messages with 20 and 26. Forwarding reference requires a deduction guide, which means C++17. But yeah, the TLDR is that moving ref can be easily backported to C++11. Future ideas. Could we prevent a reference from being used twice? And that is a question that one of you had. I almost got it working with pointer tagging. I was tagging the lower bits of the pointer, but then I realized this doesn't work. because our machines are byte addressable, and it's possible that I could have a reference to a member of an array of bytes, and so that would be a failure. I can't do that. At one point, I decided that I might make the stored pointer null and then be able to assert on whether or not the stored pointer is null because it's been moved from once. And this is an interesting aside. I was actually driving when I realized, wait a minute, this actually makes the constexpr use case worse, because with the current version, if I tried to accidentally make a constexpr moving ref, then the compiler would fail to compile because that would be a pointer to an object that was allocated at constexpr time. And so that wouldn't work. But if I reset the thing to a null pointer, then it makes the constexpr case actually worse, because now I could have a moving constexpr moving ref that happens to have a null pointer in it. And then I could just delay undefined behavior to runtime. So I didn't like that option. But there's some kind of solution in here somewhere. I thought about having a taken references count, which could be a fascinating way to debug this, but I didn't like the extra overhead that that would have, that I had to increment this taken references thing each time, plus it would double the size of a reference, which is kind of a weird concept in the first place. So I didn't go down that road. So it's just another thing to explore potentially. I could have the object layout change depending on whether or not it was compiled with in-debug. So if you're in a debug build, then it counts the references taken, but I really didn't like that idea either, so I didn't do that. But as we already saw with the Clang lifetime bound, this is worthy of basically every keyword that you have. Throw every keyword, every attribute, every decoration on it if you do something like this. How does the lifetime extension of a temporary work with moving ref? It might? No, it wouldn't work. It wouldn't work because I take a pointer, but if I took a reference internally, then lifetime extension rules can apply transitively to members of classes, but that's a really esoteric rule in the standard. I've only encountered it once, and that's when I was preparing a talk. It was a CVPCon talk a long time ago. I don't remember the name of the talk even right now. Oh, no, it was Surprises in Object Lifetime, where I explored that possibility. All right, remember, and avoid move if you can. You know, a lot of you said avoid move semantics, and I just want to agree with you, right? I want to make sure that we cover this. If you are doing something like this, where you have some object and then you immediately move it into another function, just stop doing that. Just pass the result of that, pass that object directly to the other function. Key takeaway that I really want you to take away from this: next time you identify a problem, use your imagination. A stronger type is likely to help solve that problem. So this is my talk, and if you want to reach out to me, you can go here, and we will see each other in Gather Town in just one moment. So thanks everyone for coming.